I want to talk about the Fibonacci sequence. The Fibonacci sequence is one of the most influential sequences in mathematics. It's a very simple one. We've actually already seen it in this class, but we'd like to study it. It's something where they have, there's a specific research journal that only looks at weird results with a Fibonacci sequence. It's the type of sequence that appears for a very weird reason very often in nature. So if you count the little things that stick up of a pine cone, you follow around some of the special spirals, you often get Fibonacci numbers. If you look at sunflower seeds, sunflower things as well, you often get Fibonacci sequence numbers. You often with plants, the number of flowers, they usually come in Fibonacci sequence numbers. So there's a whole lot that is surprisingly common when it comes to the Fibonacci sequence and the rest of nature. But let's take a look at some information about how it's defined and things that we can prove about it. So this is defined by the first term is 1, the next term is 1, and then every other term is found by adding the two previous. So we saw this example already. So let's just work through really quickly about some of the numbers. So we have 1, 1, 2, 3, 5. F sub 6 would be 8, and so on and so forth. So we can list off all of these by just adding the two previous terms to get the next term. So we can prove some fun facts about this. This is why there's an entire journal about it, is because there's a lot that you can prove about these. So let's see this one. That if you want to find the n plus 6 term, you can take the n plus third term, multiply by 4, and then add on the nth term. So you can look at kind of this weird type of recurrence. How we can prove this is we're just going to work with this recursive sequence and just eventually manipulate it enough until you get something that works. So how this proof works, the proof is going to be very computational. It's just going to be one giant slew of computations. So we will say, notice, f sub n plus 6. So we're going to work with this and show how do we eventually get the right-hand side. So what I know from the Fibonacci sequence is that to find the n plus 6 term, I can add on the two previous terms of f sub n plus 5 plus f sub n plus 4. Now, I'm not interested in n plus 5 and n plus 4. I'm interested in n plus 3 and n. So I'm going to use information that I know about n plus 5 and n plus 4 to get closer to things about n plus 3 and n. So I could rewrite this now as f sub n plus 4 plus f sub n plus 3. So I know that f sub n plus 5 is this. So what I have done is I've replaced this term with this. Now here, f sub n plus 4, I could replace that with smaller terms as well. This would be f sub n plus 3 plus f sub n plus 2. Now, these terms are great, right? We want the n plus 3s. This term's kind of necessary, right? Because it just had to appear for this one to get broken down. But this one, I can start to reduce this one further. So I could write this first one as f sub n plus 3 plus f sub n plus 2. These two terms I'm going to combine as just 2 times f sub n plus 3 plus f sub n plus 2. So I'm going to combine all of my terms of similar subscripts. So I have 3 times f sub n plus 3 plus 2 times f sub n plus 2. So this is starting to get a little bit closer to what we want. Now, obviously, we're missing another copy of n plus 3, but we also don't want n plus 2. I want there to be other terms. So I'm going to keep one of those around and see what happens. Okay. So I have 3 times f sub n plus 3 plus f sub n plus 2, and then I'm going to now rewrite this other one as f sub n plus 1 plus f sub n. So I just broke down one of these into the previous two terms. Now notice I have the f sub n there, that's cool. I have 3 copies of this. So what I'm missing is another copy of f sub n plus 3. But I have these two terms. So notice these two terms, when you add them together, gives you f sub n plus 3. So what this becomes is 3 times f sub n plus 3 plus f sub n plus 3 plus f sub n. And so combining all of this, I get 4 times f sub n plus 3 plus f sub n. And that's it. The proof is entirely computational in nature. It's just simply using the recursive definition and just following through the steps. So these, I mean, they can become pretty addicting when you start to find other patterns that emerge. So you could look, I mean, you could try to create some on your own. Say, what happens if I add every other term together? So if I add 1 plus 2, I get 3. If I add 1 plus 2 plus 5, that will give me 8. If I keep going on, so for instance, f sub 7 would be 13, f sub 8 would be 21, f sub 9 would be 34. So if I add 1 plus 2 plus 5 plus 13 together, well, then I get 1 plus, this gives me 3, plus 5 gives me 8, plus that gives me 21. So you could find some cool patterns if you continue to play around with these. Again, you could try, what if I instead add the other ones together? So I add this to get 4. I add this one on, I get 12. I add this one on, I get 33. Well, now I get slightly different patterns, but these numbers seem a little bit surprising to appear. So if you want, I would suggest take some time, mess around with the sequence. It's really interesting. And then if you want to just watch a whole bunch of videos, you could go down a whole rabbit hole about all different types of crazy Fibonacci videos. Feel free to look on YouTube for those. But it's a really cool sequence, and we're going to do another video based off of the closed formula.